In 2010, a telescope buried in Antarctic ice picked up a faint shadow in the microwave background, a cold smudge in the sky that most people never heard about. 6 years later, a paper that almost nobody read ran the numbers on what was sitting at the center of that shadow. The answer was 100 billion suns, one single object. 100 billion times the mass of the star our entire civilization orbits. It is so large that if placed where our sun sits, it would swallow Earth, Mars, Jupiter, Pluto, the heliopause Voyager 1, and reach almost 2,000 astronomical units into the inner Oort cloud. And here is the thing that should keep you up at night. That number is not the strangest fact about it. The strangest fact is that something this size is, on average, less dense than the air you are breathing right now. If you want to understand how that is physically possible, and what it tells us about the actual upper limit of what the universe is allowed to build, settle in. This one is worth your full attention. If you are new here, make sure to hit like and subscribe. Now, settle in and let's ease into this one slowly. Part 1. The object hidden in a cluster nobody noticed. There is a patch of sky in the southern constellation Phoenix that, for most of human history, looked like nothing at all. No bright stars, no obvious structure, nothing that would catch the eye of anyone scanning the heavens on a clear night. And for a long time, that was exactly the scientific consensus, that whatever sat in that direction was unremarkable, distant, and probably not worth a second look. Which is funny, in a way, because what was sitting in that direction turned out to be the single most extreme object ever catalogued in the known universe. An object so massive that the number describing its weight requires you to stack 100 billion suns on top of each other just to get in the right ballpark. An object whose outer boundary, not its center, its outer boundary, would swallow our entire solar system and reach into the beginnings of interstellar space. But in the year 2010, nobody knew that yet. Nobody even had a name for the thing. What they did have was a telescope buried in Antarctic ice. The South Pole Telescope is not the kind of instrument most people picture when they think of astronomy. It does not sit on a mountain. It does not have a dome. It is a 10-meter dish planted at the geographic South Pole, specifically designed to scan the cosmic microwave background, that faint, almost uniform glow of radiation left over from the earliest moments after the Big Bang. The instrument is extraordinarily sensitive to small temperature fluctuations in that background radiation, and it was during a systematic survey of the sky in 2010 that it flagged something unusual in the Phoenix constellation region, a distortion, a shadow, in a sense, a place where the microwave background appeared slightly cooled compared to its surroundings. This effect has a name. Astrophysicists call it the Sunyaev-Zeldovich effect, after the two scientists who predicted it in 1969. Here is the basic idea. Galaxy clusters, those enormous gravitational cities containing hundreds or thousands of individual galaxies, are filled with incredibly hot gas. That gas is not just floating there passively, it is actively interacting with the photons of the cosmic microwave background as they pass through. When those photons collide with the hot electrons in the cluster gas, they receive a small energy boost, which shifts them to slightly higher frequencies. From the perspective of an observer on Earth, this means the microwave background looks slightly cooler in the direction of the cluster. The photons have been kicked up the energy spectrum, leaving a subtle cold spot in the microwave map. It is a delicate effect. The temperature shift involved is measured in millionths of a degree, but for the South Pole Telescope, which had been designed specifically to detect these kinds of subtle imprints on the cosmic background, it was a clear signal, the unmistakable fingerprint of a massive galaxy cluster, sitting approximately 5.7 billion light-years away. The object was given the catalogue designation SPT-CLJ 234 4-4243. Not exactly a name that rolls off the tongue. It would eventually become known as the Phoenix Cluster, partly because of its location in the Phoenix constellation, and partly, as it turned out, because of something phoenix-like in its behavior, a suggestion of processes either dying or being reborn at its center in ways that astronomers did not initially understand. But at the moment of detection, it was simply an entry in a survey catalogue, a signal in the noise, a designation, and then the follow-up observations began. When X-ray telescopes were pointed at the Phoenix Cluster's coordinates, primarily using the Chandra X-ray Observatory and the European XMM Newton satellite, what came back was not what the astronomers expected. The cluster was luminous, extraordinarily luminous in the X-ray spectrum, far beyond the typical brightness expected for even a large, massive cluster. The hot gas filling the cluster, that intracluster medium that had produced the Sunyaev-Zeldovich signal, was radiating energy at a rate that immediately stood out as anomalous. In a typical galaxy cluster, the hot gas reaches a kind of equilibrium. It radiates some energy, yes, but the rate at which it loses heat is balanced well enough by various heating mechanisms that the system more or less maintains its structure over cosmic time. The gas cools, but slowly, gently, in a controlled way. That was not what was happening inside SPTCLJ 2344-4243. The X-ray luminosity data told a different story. The gas at the cluster's core was not cooling slowly and gently. It was cooling at a rate that, when the astronomers ran the numbers, came out orders of magnitude above what would be considered normal for a cluster of this type. The core was not in equilibrium. It was losing energy at a prodigious rate, and that energy loss meant that the gas was doing something that hot gas in galaxy clusters is generally discouraged from doing. It was falling inward, collapsing toward the center under its own gravity, with nothing to stop it. This, in the language of astrophysics, is a cooling flow, and cooling flows are supposed to be self-limiting. They are supposed to trigger a feedback response from the central engine of the galaxy that sits at the cluster's core. But in the Phoenix cluster, something about that feedback response was either absent or catastrophically insufficient. The gas was pouring toward the center like water going down a drain, and the question that immediately presented itself was not merely interesting, it was fundamental. What was sitting at the center of this cluster that was both powerful enough to show signs of massive energy output and yet somehow failing to stop a runaway infall of cosmic proportions? The answer, as it would turn out over the next several years of increasingly detailed observations, would require rethinking the upper boundary of what a black hole is even allowed to be. But in 2010, the cluster was just a bright anomaly, a system that seemed to be failing to stabilize, a signal that something extraordinary was happening at the center of a galaxy nobody had bothered to name. That extraordinary something had been sitting there for billions of years. It had been sitting there while our solar system formed, while life appeared on Earth, while the entire history of human civilization played out in its entirety, and it had not moved, had not announced itself, had not shown up on any visible light photograph of the sky in any obvious way. It was hidden inside a cloud of X-ray emitting gas, 5.7 billion light-years away, patiently radiating its signature into the cosmos and waiting for something sensitive enough to notice. The South Pole Telescope noticed, and once the follow-up data started coming in, the question of what was at the center of that cluster became one of the most pressing puzzles in observational astrophysics. Part 2. The cooling flow that refuses to stop. Let us take a moment to appreciate how strange the Phoenix cluster's central region actually was, because the phrase cooling flow does not quite do justice to what was being observed. In a typical massive galaxy cluster, the intracluster medium, that enormous reservoir of gas filling the space between galaxies, sits at temperatures measured in tens of millions of degrees. It is plasma, not ordinary gas in any familiar sense. It is so hot that atoms cannot hold on to their electrons, so everything exists as a soup of bare nuclei and free electrons crackling with thermal energy. At these temperatures, the gas radiates X-rays, and it does so continuously. The cluster glows in X-ray light as a result of this radiation, and the rate at which it loses energy through that radiation determines how quickly it cools. For most clusters, that cooling is slow enough that it barely matters on human timescales. The cluster gas in a typical system takes longer than the current age of the universe to cool significantly. It is almost static, thermally speaking, a vast, hot, slowly pulsing reservoir of plasma that has barely changed in billions of years. The Phoenix cluster was cooling at roughly 2,000 solar masses of gas per year. Stop and let that number settle. 2,000 suns worth of material, 2,000 times the mass of an entire star, was completing the transition from hot, diffuse, X-ray emitting plasma to something colder and denser every single year, not over billions of years per year. This was not a slow geological cooling process. This was a catastrophic runaway infall that showed no sign of stopping, and every sign of having been going on for an extended period of cosmic time. To understand why this matters, you need to understand what is supposed to happen in this kind of situation. The standard picture, the one that had been well established by observations of dozens of other galaxy clusters, goes something like this. Gas cools in the cluster core. As it cools, it begins to fall inward under gravity. As it falls inward, it feeds the central galaxy. The central galaxy contains an active galactic nucleus, a supermassive black hole at its center that is actively consuming material. As that black hole eats, it generates enormous jets of energy that blast outward into the surrounding cluster gas, reheating it, disrupting the infall, and restoring the thermal balance of the system. This is called AGN feedback, and it is one of the most important regulatory mechanisms in the universe for controlling how galaxies and galaxy clusters evolve. The black hole acts as a thermostat. Gas cools, falls in, heats the black hole's accretion environment. Black hole fires jets. Jets reheat the gas. Cooling slows down. Balance restored. The Phoenix cluster had apparently never received this memo. Radio observations of the central galaxy. By this point, the cluster had been observed across the entire electromagnetic spectrum, from X-ray through radio, showed that the AGN at its center was not inactive. It was producing jets. The jets were doing what jets are supposed to do, carving out cavities in the surrounding hot gas, pushing bubbles of relativistic plasma into the intracluster medium. From the perspective of the feedback mechanism, the central engine was doing its job, and yet the cooling flow continued. The gas continued to fall inward at that extraordinary rate of thousands of solar masses per year, brushing aside the AGN feedback as if it barely registered. The system was not in the standard feedback equilibrium. It was not even close. Something about the balance of forces in the Phoenix cluster's core had tipped decisively in favor of cooling and infall, and the AGN jets, despite their obvious presence and energy output, were not sufficient to arrest the collapse. This was confirmed dramatically when the Atacama Large Millimeter Array, known as ALMA, was used to observe the cluster's core at millimeter wavelengths, sensitive to cold molecular gas rather than hot plasma. What ALMA found was extraordinary. Filaments of cold molecular gas, stretching 10 to 20 kiloparsecs from the central galaxy, roughly 30 to 65,000 light-years, in long, tendril-like structures extending outward from the core and then curving back inward. These were not random wisps of material. They had coherent structure. They flowed. They looked, in the false color images produced from the data, like rivers, great cosmic rivers of cold molecular material, channeling gas from the cooling intracluster medium back toward the center of the galaxy. The metaphor of rivers is apt and not accidental. The gas in these filaments was at temperatures of only a few tens of Kelvin, barely above absolute zero compared to the tens of millions of degrees of the surrounding plasma. It had made the extraordinary journey from hot X-ray emitting plasma all the way down to cold molecular cloud in what, cosmically speaking, was an eye blink of time. And then it was flowing back toward the center, feeding into the galaxy's star-forming regions, and ultimately toward whatever was sitting at the galaxy's very core, because the star formation rates being measured in this central galaxy were not normal either. Optical and ultraviolet observations were showing star formation proceeding at a rate of hundreds to well over 1,000 solar masses per year. In context, the Milky Way, our own galaxy, forms stars at a rate of roughly 1 to 3 solar masses per year. The central galaxy of the Phoenix cluster was making new stars at a rate somewhere between 300 and 1,000 times higher than our entire galaxy. It was one of the most intensely star-forming objects ever identified, and it was forming stars not because it had somehow acquired an unusual supply of raw material from outside. It was forming stars because the cooling intracluster medium was delivering raw material to it faster than it could convert it to stars. This is what a feedback near-collapse regime looks like in practice. The cluster was simultaneously showing clear signs of AGN activity. The jets were there, the cavities were there, the radio bubbles were there, and yet the cooling flow was running away. The star formation was proceeding at an absurd pace. The molecular filaments were feeding the center. The system was stable enough not to have blown itself apart, but unstable enough that the standard equilibrium picture simply did not apply. Two competing forces were operating in the Phoenix cluster's core simultaneously, and neither one was winning decisively. Cooling and infall on one side, AGN heating and feedback on the other. The system existed in a state of dynamic tension, like a tug-of-war between two evenly matched teams, except that both teams were pulling with forces measured on galactic scales, and the rope between them was a river of molecular gas 2,000 light-years across. This raised an immediate and uncomfortable question. If the AGN at the center of this system was already doing everything a powerful active galactic nucleus is supposed to do, firing jets, inflating radio bubbles, pushing back against the inflow, and the cooling flow was still running away, then how powerful did the engine at the center actually have to be? How massive did a black hole need to be to have both this level of AGN output and still be insufficient to shut down the infall? The numbers, when they were eventually worked out, were going to be shocking. But to get to the numbers, someone first needed to build the right mathematical framework. And that would take until 2016, when a paper buried in the pages of astronomy and astrophysics quietly changed the scale of what we thought the universe was capable of producing. Part 3. The paper that quietly changed the scale of the universe. In 2016, a team of researchers led by Michael Brockamp published a paper in the journal Astronomy and Astrophysics. The title was Unveiling Gargantua. It was not widely reported in the mainstream press. It did not generate the kind of media coverage that, say, the first Event Horizon Telescope image of M87 would generate 3 years later. It landed in the academic literature, accumulated citations among specialists, and largely stayed there. A technical result in a technical journal, noted by the people who needed to note it, and mostly invisible to everyone else. The conclusion of that paper was that the black hole at the center of the Phoenix cluster had a mass of approximately 100 billion solar masses. 100 billion suns compressed into a single gravitational singularity. Not a million, not a billion. 100 billion. The number is written in scientific notation as 10 to the power of 11 solar masses, and when you write it out in full, it looks like this: 100,000 million times the mass of the star that every planet in our solar system orbits. That is the number Brockamp and colleagues arrived at, and it sits at the upper edge of what any astrophysicist, working from first principles, would have expected to be physically plausible for a black hole in the current universe. How did they get there? The method is worth understanding because it is central to one of the most important caveats attached to Phoenix A's mass estimate and to the broader story of what Phoenix A actually is and what it means. Brockamp and colleagues did not use stellar orbits the way the Galactic Center team that won the Nobel Prize in Physics in 2020 did for Sagittarius A star. They did not use direct radio imaging the way the Event Horizon Telescope did for the black hole in M87. Those methods, direct dynamical measurement and direct imaging, are the gold standards of black hole mass estimation. They give you numbers tied directly to observable physics with well-understood uncertainties. What Brockamp and colleagues did instead was something more indirect, more inferential, but in its own way more ambitious. They used the cluster itself as the measurement instrument. The logic runs as follows. The Phoenix cluster's central AGN is dumping enormous quantities of energy into the surrounding gas. Those jets, those radio bubbles, those cavities in the X-ray gas, all of that represents real, measurable energy output. The amount of energy required to inflate those cavities against the pressure of the surrounding plasma can be calculated directly from the observed cavity sizes and the measured pressure of the gas. This gives you the mechanical power output of the AGN in physical units, watts, essentially, though the numbers involved are so large that astrophysicists tend to express them in terms of solar luminosities or ergs per second. At the same time, the cooling flow rate gives you the energy input to the system from the infalling gas. 2,000 solar masses of gas per year falling into a gravitational potential of the depth and size measured in the Phoenix cluster represents an enormous rate of gravitational energy release. The gas loses energy as it falls, and that energy ultimately feeds the AGN. The relationship between the mass accreted, the energy released, and the efficiency of the conversion process is governed by physics that is reasonably well understood, at least in broad terms. If you know how much energy the AGN is putting out, and you know the efficiency with which it converts accreted mass into energy, you can work backward to the accretion rate. And if you know the accretion rate and the mass ratio relationships that govern how black holes grow relative to the stellar masses of their host galaxies, relationships that had been calibrated across hundreds of other systems, you can estimate the black hole mass. The result, combining cooling flow rate analysis, AGN feedback energy output calculations, and stellar dynamics constraints from the central galaxy's measured properties, was a mass of approximately 10 to the power of 11 solar masses, 100 billion suns. It is important to be clear about what this method involves, because the uncertainty it introduces is not trivial. The efficiency assumption is critical. The conversion of accreted mass into radiated energy in an AGN is not 100%. It is not even close to 100%. Typical assumed efficiencies run between about 5 and 40%, depending on the physical model, and the exact value has an enormous effect on the derived mass. If the efficiency is higher than assumed, the black hole is lighter. If it is lower, it is heavier. The inferred mass of 10 to the 11 sits at the intersection of a set of model-dependent choices, not at the output of a direct measurement. This is not a flaw unique to the Phoenix A analysis. Indirect mass estimates for black holes in distant or heavily obscured systems are almost always model-dependent to some degree. The question is whether the model is well constrained enough by independent data points to give a reliable result. Brockamp and colleagues argued that the combination of constraints, cooling flow, AGN output, and stellar dynamics was tight enough to support their conclusion within the stated uncertainties. Other researchers in the field have been more cautious, with some suggesting that the true mass might sit in the range of 10 to 20 billion solar masses rather than 100 billion, and others finding the 100 billion estimate within plausible bounds. What did the paper do to the rankings? Prior to unveiling Gargantua, the default answer to the question of what the largest known black hole was would typically have been TON 618, a quasar located roughly 10.4 billion light-years away, with a mass estimated at around 66 billion solar masses, derived from single-epoch virial mass estimation of its broad emission lines. TON 618 is a remarkable object. Its mass, while similarly indirect in its derivation, has been widely accepted as placing it near the upper end of the observed black hole mass distribution. Other candidates in the same extreme mass range include Home 15A star, the black hole at the center of the galaxy NGC 1277, and a handful of others clustered in the range of 10 to 40 billion solar masses. Phoenix A, at the Brockamp estimate, sits above all of them. But here is the thing that gives every serious astrophysicist pause when discussing the Phoenix A mass estimate. Unlike TON 618, unlike M87, unlike even Sagittarius A star, the black hole 4 million solar masses in the center of our own galaxy, Phoenix A has never been directly measured in any way. No stellar orbits have been traced around it. No direct imaging has been achieved. The Event Horizon Telescope has not yet pointed at it with sufficient resolution to resolve its shadow. It exists, for now, entirely as an inference, a conclusion drawn from the behavior of the cluster that surrounds it, filtered through models that carry real and non-trivial uncertainties. In a field that prides itself on direct observational evidence, Phoenix A is unusual. It is defined not by what we can see, but by what we cannot explain without it. It is, in the most literal sense, a black hole, invisible, unimaged, unmeasured, and the only reason we know it is probably there, and probably enormous, is that the galaxy cluster wrapped around it is behaving in ways that require something of that magnitude at its center, which raises a question that the Brockamp paper, quietly and almost in passing, placed on the table of astrophysics. If an object of 100 billion solar masses can exist, if the universe really does build things on this scale, then where is the upper limit? Is there one? And if Phoenix A sits near the ceiling of what black holes can become, what does the view from that ceiling look like? To answer that, you first need to understand just how enormous the thing actually is, and for that, you need to leave the realm of solar masses and enter the realm of geometry. Part 4. Phoenix A star, the unmeasured giant. There is a particular kind of discomfort that comes from trying to hold Phoenix A star in your mind as an object. It is not that the number is too large, exactly. Astronomers work with large numbers constantly. 1 billion solar masses, 1 trillion stars, distances measured in megaparsecs. These quantities appear regularly in the literature, and people who work with them professionally develop a kind of functional relationship with scales that would otherwise be paralyzing. The discomfort with Phoenix A star is different in character. It comes from the fact that the object exists at a peculiar intersection of certainty and uncertainty that is unusual even by the standards of extreme astrophysics. Consider what we know for certain. There is a galaxy cluster at the coordinates designated SPT CLJ 2344-4243, sitting approximately 5.7 billion light-years from Earth. At the center of that cluster is a massive galaxy. At the center of that galaxy is an active galactic nucleus. That much is directly confirmed by observations across multiple wavelengths using multiple independent instruments. There is definitely something there. There is definitely an engine of some kind at the center of this system. Now consider what we do not know directly. We do not know the mass of that engine. We have not measured it using stellar orbital dynamics. We have not imaged its shadow against the backdrop of surrounding radiation. We have not done the kind of a direct, model-independent measurement that would give us a mass with the confidence we attach to, say, the 40 million solar mass estimate for M87, which comes with the backing of both a direct image and a resolved shadow, whose angular size is tied to the mass through well-understood physics. What we have for Phoenix A star is indirect. It is inferred. It is the output of a model applied to cluster-scale observations and filtered through efficiency assumptions. Contrast this with the two most famous black holes in contemporary astrophysics. Sagittarius A star, the black hole at the center of the Milky Way, has a mass of approximately 4 million solar masses, and we know this because we have spent decades tracking the orbits of individual stars moving around it at close range. The star called Stu, for example, has an orbital period of about 16 years and comes within 120 astronomical units of Sagittarius A star at its closest approach. By watching that star move and applying Kepler's laws of orbital motion, the mass of the central object is derived as directly as any astronomical measurement can be. The Nobel Prize in Physics in 2020 was awarded partly for this work. M87 star, the black hole, whose image was released by the Event Horizon Telescope collaboration in April 2019, sits in the center of the galaxy, M87, about 55 million light-years away, with a mass of approximately 6.5 billion solar masses. The EHT image is the direct observation of photons bending around the object's event horizon, producing the characteristic bright ring around a central shadow. The shadow size is tied to the mass through general relativity, with an uncertainty of roughly 10 to 15%. This is a direct image of a black hole's gravitational footprint. Phoenix A star has neither of these things. It is too far away for the current EHT to resolve its shadow at the resolution required. The stars near its center cannot be individually tracked from Earth at a distance of 5.7 billion light-years. And so, its mass estimate sits in a different epistemic category from the masses of Sagittarius A star and M87. Not less important, but less certain. Not implausible, but not yet confirmed at the same standard. The community is not unanimous on whether the Brokamp estimate is correct. Some astrophysicists working on the mass-velocity dispersion relations that connect black hole masses to the properties of their host galaxies suggest a somewhat lower value, perhaps in the range of 20 to 40 billion solar masses, based on the host galaxy's stellar velocity dispersion, which itself is a somewhat uncertain measurement for an object this distant. Others, working from the cluster energetics side, find the 100 billion estimate broadly consistent with the data. The range of honest uncertainty spans roughly an order of magnitude, which in black hole astrophysics is not unusual for an indirectly measured object. And yet, and this is the key point, even at the lower end of that uncertainty range, Phoenix A star remains one of the most extreme objects ever identified. A black hole of 20 billion solar masses would still substantially exceed M87 star in mass. A black hole of 40 billion solar masses would still place Phoenix A star at the very top of any observationally grounded ranking of ultramassive black holes. The debate is not about whether Phoenix A star is enormous. It is about how precisely enormous, and whether the specific claim of 100 billion solar masses is supported by the available evidence at a confidence level the field typically requires. For the purposes of thinking about what this object actually is, what it means physically, geometrically, and cosmologically, the exact mass matters somewhat less than the order of magnitude. And the order of magnitude is not seriously in dispute. Phoenix A star contains somewhere between tens of billions and 100 billion solar masses in a region of space-time that we are going to need a new vocabulary to describe. Which brings us to the question of what those tens of billions to 100 billion solar masses look like as a piece of geometry. Because a black hole is not, in the standard sense, a physical object with a surface you could touch or a shape you could observe. It is a region of space-time, and the boundary of that region, the event horizon, has a size that is tied directly through the mathematics of general relativity to the mass inside it. If Phoenix A star's mass is 100 billion solar masses, then its event horizon is not measured in meters or kilometers or even astronomical units. It is measured in light days and light weeks. And when you calculate that number and start laying it against familiar reference points in our own cosmic neighborhood, you begin to understand why the people who study this object sometimes pause mid-sentence and just sit with the arithmetic for a while. Part 5. The first scale break. Let us do the calculation together, because the mathematics of black hole size is surprisingly accessible once you have the right starting point. The boundary of a black hole, the event horizon, the point of no return beyond which not even light can escape, is defined by what physicists call the Schwarzschild radius. This was first derived by Carl Schwarzschild in 1916, less than 2 months after Einstein published his field equations of general relativity in a letter written from the Eastern Front, where Schwarzschild was serving as a German artillery officer. He solved Einstein's equations exactly for a non-rotating, spherically symmetric mass, and in doing so produced the formula that defines how large a black hole of a given mass must be. The formula is elegantly simple. The Schwarzschild radius equals 2 times Newton's gravitational constant times the mass of the object, divided by the speed of light squared. For the Sun, this radius works out to approximately 3 kilometers. This means that if you could somehow compress the entire Sun, all of its mass, into a sphere 3 kilometers in diameter, you would cross the threshold into a black hole. The Sun's current radius is about 696,000 kilometers. Its Schwarzschild radius is 3 kilometers. The Sun is, in this sense, an enormously puffed-out object relative to its own black hole limit. For Phoenix A star, with a mass estimated at 100 billion solar masses, the Schwarzschild radius scales linearly with mass. 100 billion times 3 kilometers gives approximately 300 billion kilometers. 300 billion kilometers. Now let us convert that into something more useful for spatial reasoning. An astronomical unit, 1 AU, is the average distance from Earth to the Sun, approximately 150 million kilometers. 300 billion kilometers divided by 150 million kilometers per AU gives approximately 2,000 astronomical units. 2,000 AU. That is the Schwarzschild radius of Phoenix A star. Now, let us anchor that number in something familiar. Pluto's average distance from the Sun is about 40 astronomical units. So, the distance from Earth to Pluto, the journey that NASA's New Horizons spacecraft took 9.5 years to complete at a speed of approximately 58,000 kilometers per hour, that entire distance fits inside the event horizon of Phoenix A star, with room left over for 49 more identical trips. Voyager 1, the most distant human-made object in history, launched in 1977 and now traveling through interstellar space, is currently approximately 163 to 170 astronomical units from the Sunday. It has been traveling for nearly 50 years at speeds that would cross the entire United States in less than 4 minutes. It would still be inside Phoenix A star's event horizon with room to spare. The heliopause, the boundary where the Sun's solar wind is finally overcome by the pressure of interstellar gas, the technical edge of the Sun's sphere of influence, sits at roughly 120 astronomical units, also inside. Neptune, the outermost of the 8 recognized planets, orbits at approximately 30 astronomical units, inside. Jupiter, the largest planet in the solar system, orbits at about 5.2 astronomical units, inside. Mars, the focus of multiple current and planned crewed missions, orbits at about 1.5 astronomical units, inside. Earth, the only confirmed living world in the cosmos, orbits at 1 astronomical unit, inside. If you placed Phoenix A star where the Sun currently sits, the event horizon would extend outward in every direction to approximately 2,000 astronomical units, every planet, every moon, every asteroid, every comet currently on its inward journey from the outer reaches of the system, the entire Kuiper belt, which extends from about 30 to 50 AU, would be gone. The inner Oort cloud, that sparse theoretical reservoir of long-period comets that begins somewhere around 2000 AU and extends perhaps tens of thousands of AU further, would be sitting right at the boundary, right at the threshold of the event horizon, on the knife edge between escape and eternal infall. The event horizon of Phoenix A star is so large that light, travelling at just under 300,000 kilometers per second, fast enough to circle Earth 7 times in a single second, would take more than 3 weeks to travel from one side to the other. Approximately 23 days of continuous travel at the maximum speed the universe permits, just to cross the boundary of this one gravitational region. And here is the thing that makes this thought experiment more than just an exercise in large number arithmetic. The event horizon is not a physical surface. There is no wall there, no membrane, no special material. If you were somehow transported to the event horizon of Phoenix A star and crossed it, you would not feel an impact. There is no pressure wave, no thermal spike, no physical barrier of any kind. The event horizon is purely a geometric boundary, a surface defined entirely by the curvature of spacetime, beyond which the mathematics of general relativity says that all future directed paths through spacetime, including paths followed by light, lead inward. You do not crash into the event horizon. You simply pass through a region of space where the geometry has become locally indistinguishable from the geometry everywhere else, and globally inescapable. This is one of the deepest conceptual shifts required to understand black holes. The event horizon is not a thing. It is a relationship between space-time geometry and the maximum speed at which information can travel. It is defined not by what is at the boundary, but by what the boundary means for the future of anything that crosses it. From the inside, after crossing, the destination is not a wall, but a direction. The singularity is not somewhere you can avoid by steering around it. It is the future itself. Every path leads there, the way every moment in ordinary spacetime leads to the next. For a black hole the size of Phoenix A star, you would cross that boundary surrounded by what appears to be perfectly ordinary space. Stars in the distance, though not the same stars visible from outside, red-shifted and rearranged by the immense gravitational geometry. Gas, radiation, perhaps the turbulent matter of the accretion disk well outside the horizon. Nothing immediately dramatic. You have just entered the single largest zone of no return in the known universe, and the scenery at the doorstep is, in local terms, almost quiet. Almost. Because while the local experience of crossing might be unremarkable, the fact that an object on this scale can exist at all raises a set of questions that do not have clean answers. If the universe can make a black hole with an event horizon 2,000 astronomical units across, what is the upper limit? Is there one? And why does this particular object appear to sit near it? Those questions take us deeper into the territory where physics becomes less certain and more fascinating, into the domain of what we actually understand about how black holes this extreme are supposed to behave, and why the way they behave is almost exactly the opposite of what intuition would predict. Part 6. The Density Paradox. Here is a fact about Phoenix A star that should, on first encounter, feel wrong. If you calculate the average density of the region enclosed by Phoenix A star's event horizon, not the density of any matter inside it, but the average density of the entire spherical volume defined by its Schwarzschild radius, you get a number that is less than the density of air at sea level. Take a moment with that. The largest object in the known universe, an entity containing 100 billion solar masses, has a gravitational boundary that encloses a region of space with an average density lower than the air in your lungs right now. The calculation is not subtle or approximate. It follows directly from the mathematics of black holes. The average density of a black hole is defined as its mass divided by the volume of the sphere with radius equal to its Schwarzschild radius. The Schwarzschild radius grows linearly with mass, double the mass, double the radius. But volume grows as the cube of the radius, double the radius, and the volume increases by a factor of 8. This means that as black hole mass increases, the mass scales as m, while the volume scales as m cubed, and therefore the average density scales as m divided by m cubed, which gives 1 over m squared. Average density falls as the square of the mass. For a stellar mass black hole, say, a black hole formed from the collapse of a star 20 times the mass of the Sun, giving a final mass of perhaps 10 solar masses, the Schwarzschild radius is about 30 kilometers, and the average density is extraordinary. We are talking about densities, hundreds of trillions of times higher than water, higher than nuclear matter, approaching and perhaps exceeding the theoretical limits of what conventional physics can describe. These are the black holes that match the popular intuition, objects of unimaginable compactness, where matter has been squeezed so tightly that it escapes all familiar description. For a supermassive black hole at the scale of M87, with 6.5 billion solar masses, the average density is already much lower. Still significantly denser than water, but within the range of ordinary terrestrial densities rather than nuclear densities, getting less extreme. For Phoenix A star at 100 billion solar masses, the average density calculation gives a value somewhere in the range of approximately 1/100th to 1/1000th of a kilogram per cubic meter. Atmospheric air at sea level has a density of approximately 1.2 kilograms per cubic meter. Phoenix A star's event horizon volume has an average density orders of magnitude below that. If you scooped up a cubic meter of the space inside Phoenix A star's event horizon, just a random sample from some interior region far from the singularity, and brought it to a laboratory, it would weigh less than the same cubic meter of air you are breathing. In fact, it would be closer in average density to what we think of as a hard vacuum. This is not a paradox in the mathematical sense. The equations are perfectly consistent, and the result follows cleanly from general relativity. But it is a deep conceptual inversion of what black holes are supposed to be in the popular imagination. The phrase black hole conjures images of compressed matter, of density beyond comprehension, of a point where physics breaks down under impossible pressure. For stellar black holes, that picture is roughly accurate. For Phoenix A star, it is almost exactly wrong. What a black hole actually is, at its most fundamental geometric level, is not a compressed object. It is a region of spacetime in which the curvature of geometry has become steep enough that escape requires exceeding the speed of light. The matter that created it, whatever original mass fell in to build the object to its current size, has been incorporated into the spacetime geometry. The event horizon is not a container holding compressed material. It is a surface where the mathematics of curvature crosses a critical threshold. A smaller black hole crosses that threshold at a smaller radius, meaning that a large mass has to be squeezed into a small volume, meaning high average density. A larger black hole crosses that threshold at a larger radius, meaning the same density requirement is met by mass distributed across an enormous volume. The geometry cares about the relationship between the mass and the radius. As the mass grows, the required radius grows proportionally, and the geometry can be satisfied at progressively lower average densities. Phoenix A star takes this logic to its extreme conclusion. Its mass is so enormous that the geometric threshold, the point of no return, occurs at a scale so large that the average density inside it is, by terrestrial standards, negligible. It is the most extreme gravitational region in the known universe, and it contains, on average, less matter per cubic meter than a room full of air. The misconception runs deep. We talk about black holes compressing matter, and at small scales, this is a reasonable description. But Phoenix A star is a reminder that black holes are not primarily about compression. They are about geometry. They are about the shape of space-time exceeding the escape velocity of light. And geometry, it turns out, can do that just as easily by being extremely large as by being extremely dense. This leads to a consequence that most people find even more surprising than the density paradox. If the event horizon of Phoenix A star is a region of low density and mild space-time curvature, if the geometry there is, locally speaking, not dramatically different from ordinary space, then what is it actually like to cross it? Part 7. The gentle edge of a cosmic monster. There is a thought experiment that physicists use to challenge intuition about black holes, and it goes like this. Imagine you are an astronaut. You are falling freely, not in a spacecraft, not under thrust, just falling toward the event horizon of a black hole. What do you experience as you cross it? For a stellar mass black hole, the answer is immediately and definitively lethal. The gravitational gradient near the event horizon of a stellar mass black hole is so steep that the tidal forces, the difference in gravitational pull between your feet and your head, are enormous. If your feet are pointing toward the black hole and your head is pointing away from it, the black hole is pulling your feet significantly harder than your head because your feet are measurably closer to the gravitational center and the force falls off sharply with distance at that scale. This difference in gravitational force across the length of your body produces what physicists call spaghettification, the object being stretched lengthwise and compressed laterally, like a strand of pasta being slowly pulled to its limits. For a stellar mass black hole, this process would render any human being non-viable well before reaching the event horizon. You would not cross the horizon intact. For Phoenix A star, this calculation produces a result that inverts the entire picture. Tidal forces, the gradient of gravitational force across a finite-size object, scale with the mass of the black hole in the same way as average density. Specifically, tidal forces at the event horizon scale as 1 over the mass squared. Larger mass means gentler tidal forces at the horizon. For Phoenix A star's mass, the tidal gradient across the length of a human body at the event horizon is so small as to be physically unmeasurable, not uncomfortable, not slightly noticeable, unmeasurable by any instrument we currently possess. If you were a freely falling astronaut approaching the event horizon of Phoenix A star, the transition across the boundary would involve no impact, no physical sensation, no instrument reading that differed measurably from free fall through empty space anywhere else in the universe. The space-time curvature at that point is real. It is, in a global sense, the most extreme curvature in the known universe, but its local variation across the scale of a human body is negligible. You would not be stretched. You would not be heated by tidal friction. You would not collide with any surface. You would pass through the boundary of the largest zone of no return in the known universe without any direct physical indication that anything had changed. You would not know you had crossed it. This is not a failure of physics to communicate the danger. It is precisely what physics predicts. General relativity makes a sharp distinction between local and global space-time properties. The equivalence principle, one of the foundational insights that Einstein used to build general relativity, states that in a small enough region of space-time, the effects of gravity are locally equivalent to the effects of acceleration. A freely falling observer in a gravitational field does not feel the field directly, they feel weightlessness. The local curvature only becomes detectable through tidal forces, the variation of the gravitational field across the observer's finite size, and for Phoenix A star, that variation at the horizon scale is imperceptibly small. The danger of the event horizon is not local, it is topological. It is the fact that crossing it places you inside a region from which no future-directed path leads outward. Not because there is a barrier, but because the geometry of space-time itself has been configured so that all available futures lead toward the singularity at the center. The threat is not pain or impact. It is the permanent alteration of the structure of possible futures available to you. This creates what might be the deepest psychological inversion in all of astrophysics. We tend to associate danger with sensation, with pain, with the dramatic, with physical indicators that communicate threat directly to the nervous system. Phoenix A star, the most dangerous object in the known universe by some measures, announces itself at its boundary with precisely zero sensation. The most extreme gravitational region in the observable universe is, locally, the calmest place an astronaut could be. And it gets stranger, because there is a temperature dimension to this inversion as well. The theoretical physicist Stephen Hawking demonstrated in 1974 that black holes are not perfectly cold. They emit a very slow, very faint thermal radiation, now called Hawking radiation, arising from quantum mechanical effects near the event horizon. The temperature of this Hawking radiation is inversely proportional to the mass of the black hole. Larger black holes are colder. For Phoenix A star, the Hawking temperature works out to somewhere around 2 times 10 to the power of negative 23 Kelvin. This is a number so close to absolute zero that it is essentially unmeasurable. It is far colder than the cosmic microwave background, which sits at about 2.7 Kelvin. It is far colder than the coldest temperatures ever achieved in laboratory experiments, which have reached billionths of a Kelvin. Phoenix A star is, in Hawking temperature terms, the coldest object in the universe. The largest known object in the universe is also, in a specific physical sense, the coldest. Now let us sit with the full picture. Phoenix A star is the most massive single object ever catalogued. It has an event horizon extending 2,000 astronomical units. Its average density is below that of air. Its gravitational boundary is the gentlest physical threshold in the cosmos. Its temperature is colder than anything a laboratory has achieved, and it will outlive every other structure in the universe by a margin that no human language was built to express. But if this is the largest object physics can produce, why? Is this genuinely the ceiling? Or does physics simply refuse to build anything larger for reasons we have not fully understood? Part 8. The mass ceiling nobody fully understands. Something curious happens when you survey the black hole mass distribution across the universe. The numbers get large, they get very large, but they seem to cluster. They seem to accumulate in a range and then stop. Not at an absolute hard wall, perhaps, but at something that behaves like a ceiling. The observational record contains handful after handful of ultramassive black holes, objects with masses between 10 billion and perhaps 100 billion solar masses, and then, above that range, essentially nothing. This could mean one of two things. Either physics genuinely prevents black holes from growing beyond a certain scale, or black holes larger than the observed maximum exist but are invisible to current observations. The distinction matters enormously for understanding what Phoenix A star represents. The physical argument for a mass ceiling runs through the mechanism of AGN feedback, the same process we discussed in the context of the Phoenix cluster's runaway cooling flow. As a black hole grows, the AGN feedback it produces, the jets, the energy deposition into surrounding gas, becomes more and more powerful. Eventually, the argument goes, the AGN output becomes so large that it prevents further significant accretion. The black hole has essentially heated and dispersed the gas that would otherwise feed it, creating a self-regulating system that caps growth. The King model and related frameworks in theoretical astrophysics have been used to derive predicted upper limits for black hole masses based on this mechanism, and the predicted limits are broadly consistent with the observational upper envelope of a few times 10 to the 11 solar masses. Phoenix A star, at the Brockamp estimate, sits right at that predicted ceiling, not comfortably below it, not dramatically above it, but at the boundary, which is either a striking confirmation of the theoretical framework or a coincidence born of model-dependent estimation? The honest answer is that we do not know with certainty which it is. The alternative interpretation, selection bias, is also serious. The most massive black holes tend to sit in the most massive galaxies, which tend to sit in the most massive galaxy clusters, which are the rarest environments in the universe. There are only a handful of clusters comparable to the Phoenix cluster in mass and richness within the observable universe. If black holes with masses above 100 billion solar masses exist, they are likely in environments even rarer than Phoenix A**'s host cluster, and their AGN may not be active at this cosmic epoch in ways that would make them detectable. Our surveys may simply not have found them yet. What the observational record does tell us, regardless of which interpretation is correct, is that Phoenix A* represents the current observational upper bound of the black hole mass distribution. Whether it represents a physical upper limit or simply the current detection limit is an open question, but it is one of the most important open questions in the astrophysics of compact objects and galaxy evolution, because wherever that ceiling actually lies, Phoenix A* is standing near it. And that positioning connects directly to the larger story of how these monsters came to be, a story that, as observations from the new generation of telescopes have revealed, is far more strange and contested than anyone expected just a few years ago. Part 9. JWST breaks the timeline. The James Webb Space Telescope launched on December 25, 2021, and by the second half of 2022, its first science results were already rewriting textbooks. The observatory was designed in part to look at the earliest galaxies, objects forming in the first few 100 million years after the Big Bang, at redshifts so high that their light has been stretched by the expansion of the universe from ultraviolet and optical wavelengths all the way into the infrared beyond the reach of previous instruments. JWST can detect this infrared radiation with extraordinary sensitivity, and what it found when it pointed at the early universe was not what the models had predicted. It found black holes, very large black holes, in very young galaxies, at cosmic epochs when, according to standard models of black hole growth, those black holes should not yet have had time to become that large. One of the early examples that attracted significant attention was the object designated UHZ1, detected in observations of a galaxy cluster that JWST was using as a gravitational lens to peer at objects behind it. This object, which sits at a redshift of approximately 10, meaning we are seeing it as it existed when the universe was only about 450 million years old, appeared to contain a black hole with a mass of tens of millions of solar masses. At a time when the universe was less than 5% of its current age, this black hole was already enormous by the standards of what standard accretion models would predict for that epoch. The galaxy designated GNZ11, another early universe object, showed characteristics consistent with an unusually massive central black hole for a galaxy of its size and age. The broader population of what observers began calling little red dots, compact, red-colored sources discovered in JWST imaging that appeared to be overmassive black holes sitting in host galaxies far lighter than expected, suggested that the problem was not limited to a few anomalous objects. It appeared to be a systematic feature of the early universe that the models were missing. This connects directly to the story of Phoenix A*, because Phoenix A*, at an estimated mass of 100 billion solar masses, represents a potential endpoint of black hole growth, and the problem exposed by JWST operates at the other end of the timeline. If the seeds of these monster black holes were already anomalously large in the early universe, and if Phoenix A* represents the maximum mass to which those seeds could grow over cosmic time, then the formation history connecting those two endpoints is the part we understand least well. Standard black hole growth theory posits that the supermassive black holes we see in galaxy centers today grew from smaller seeds through a combination of gas accretion and mergers. The seeds could be remnants of the first generation of massive stars, so-called population 3 stars, hypothetically forming at masses hundreds of times the Sun's mass from the primordial hydrogen and helium of the early universe, collapsing to leave black hole remnants of 100 to 1,000 solar masses. Those seeds then grow through the Eddington limited accretion process, where the maximum accretion rate is set by the balance between radiation pressure and gravity, and merge whenever their host galaxies merge. The problem is time. The universe at redshift 10 is less than 500 million years old. Growing a black hole from a stellar mass seed to tens of millions of solar masses in that time requires either sustained Eddington limit accretion from the very beginning, which is difficult to arrange in practice because the supply of gas is not always available, or episodes of super Eddington accretion, where the accretion rate temporarily exceeds the standard theoretical limit. Or, alternatively, the seeds were not stellar remnant black holes at all. They were something else. The most discussed alternative is direct collapse black holes. In this scenario, under specific conditions in the early universe, regions of intense radiation that prevent the gas from cooling and fragmenting into individual stars, an entire massive gas cloud collapses directly into a black hole without ever passing through a stellar phase, producing a seed of 10,000 to 1 million solar masses in a single event. This kind of seed starts the growth process much further along the mass scale, making it easier to reach the observed masses by early cosmic epochs. Other proposals include primordial black holes formed not from the collapse of any astrophysical object, but directly from density fluctuations in the very early universe, possibly during or immediately after the Big Bang. If primordial black holes of large mass formed early enough and in sufficient numbers, they could provide the seed population from which today's ultramassive black holes grew. The idea is speculative and contested, but JWST's early results have given it renewed attention. What this all means for Phoenix A star is that the object sits at the end of a formation pathway we do not fully understand. Its mass of 100 billion solar masses represents the accumulated result of billions of years of growth, accretion, mergers, the digestion of entire galaxies, starting from a seed whose nature we cannot currently observe directly. JWST has shown us that the seeds were already anomalously large early on. Phoenix A star shows us how large the endpoint of that process can be. The physics connecting those two endpoints, the growth history, the accretion rates, the merger chains, the feedback regulation, is one of the central unresolved problems in modern astrophysics, and it is a problem that Phoenix A star, as the most extreme known data point, makes more urgent and more pointed. Part 10. The measurement problem. It is worth pausing here before the full implications of Phoenix A star's scale and nature are laid out, to be honest about what we do and do not know with confidence. The claim that Phoenix A star is the largest black hole in the known universe rests on an inference, not a direct measurement. The Brokamp estimate of 100 billion solar masses is derived from cluster energetics modeling, and it carries uncertainties that are not trivial. Other methods, including the mass-velocity dispersion relation applied to the host galaxy, suggest somewhat lower values, potentially in the range of tens of billions of solar masses rather than 100 billion. The object's true mass, measured to the same precision as M87 or Sagittarius A star, is not currently known. This uncertainty is not unique to Phoenix A star. The ranking of ultramassive black holes by mass is genuinely unstable. Home 15 A star, the black hole at the center of the galaxy, Home 15A, which sits at the center of the galaxy cluster Abell 85, has a more directly measured mass of approximately 40 billion solar masses, derived from stellar dynamical modeling making it one of the most reliably measured objects in this mass range, and a serious contender for the actual record depending on the assumptions applied to the Phoenix A estimate. 2.618. The quasar, with a commonly cited mass of about 66 billion solar masses, uses single-epoch virial mass estimation from broad emission lines, a technique that can carry uncertainties of a factor of 2 or more in either direction. The instability of the rankings points to something important about what the phrase largest black hole actually means and how carefully it should be qualified. It is not a fixed, catalogued, unambiguous record in the way that the tallest mountain or the deepest ocean trench are fixed records. It is the current best estimate from a set of methods that carry real systematic uncertainties applied to objects that are often too distant, too embedded in complex environments, or too faint to measure directly with confidence. Phoenix A star may well be the most massive black hole in the observable universe. The Brockamp estimate may be correct, and if it is, the object's mass exceeds all competitors by a substantial margin. But the honest statement is that Phoenix A star is the object that currently occupies the high end of the possible upper bound of the black hole mass distribution, based on indirect but physically motivated modeling of its host cluster's energetics. That is a meaningful and important statement. It is just not the same statement as "we have directly confirmed this is the record holder." What is not in doubt is the scale of the object relative to everything familiar in our solar system and stellar neighborhood. Whether the mass is 50 billion or 100 billion solar masses, the event horizon is measured in hundreds to thousands of astronomical units. The object is, by any reasonable definition, extreme at a level that qualitatively separates it from familiar astrophysical objects. And it is that qualitative extremity, the consequences of being an object of this mass in the cosmos, that becomes important when we think about what it means for the long-term future of the universe. Part 11. The object that outlives everything. Let us talk about time in a way that most science communication does not, because the timescales relevant to Phoenix A star's future make the age of the universe look like a rounding error. The universe is approximately 13.8 billion years old. In scientific notation, that is roughly 1.4 times 10 to the 10th years. Write it out, and it is 13,800 million years. This feels like an incomprehensibly long time when measured against human experience. The entirety of recorded human civilization spans roughly 5,000 years, 1/3 of the current age of the universe. The age of the Earth is about 4.6 billion years, roughly a third of the universe's age. These are the scales that normally overwhelm human intuition about time. Phoenix A star will outlive the current age of the universe by a margin so enormous that the universe's current age is not even a meaningful fraction of Phoenix A star's expected lifespan. This follows from Hawking's calculation of black hole evaporation. In 1974, Stephen Hawking demonstrated that black holes are not perfectly black. They emit a slow, faint radiation, arising from quantum effects near the event horizon. The mechanism involves virtual particle-antiparticle pairs that continuously appear and annihilate throughout spacetime due to quantum uncertainty. Near a black hole's event horizon, occasionally one of these pairs appears with one particle inside the horizon and one outside. The one inside falls inward, the one outside escapes. From the black hole's perspective, it has lost a tiny amount of energy. The infalling particle has negative energy, reducing the black hole's mass ever so slightly. Over time, this process causes the black hole to slowly evaporate. The timescale for this evaporation scales as the cube of the black hole's mass. Larger black holes evaporate far more slowly than smaller ones, for the same reason that their Hawking temperature is lower. For a stellar mass black hole of 10 solar masses, the evaporation time is approximately 2 times 10 to the 74th years, 2 with 74 zeros after it. For a supermassive black hole like M87, the timescale is vastly longer, on the order of 10 to the 93rd years or more. For Phoenix A star, at 100 billion solar masses, the evaporation timescale is approximately 10 to the 107th years, or, expressed differently, 10 million googles of years, where a google is one with 100 zeros after it. This number is not just larger than the current age of the universe. It is larger than the age of the universe raised to the power of 10 multiple times over. It has no meaningful analogue in human language or experience. But there is more complexity even within this extreme timescale. At the current epoch, Phoenix A star is not actually shrinking, it is growing. The cosmic microwave background, that 2.7 Kelvin glow that permeates all of space, represents a bath of thermal photons that any black hole is embedded in. If the Hawking temperature of the black hole is lower than the temperature of the surrounding CMB, then the black hole absorbs more radiation from the CMB than it emits via Hawking radiation. Phoenix A star's Hawking temperature is approximately 10 to the negative 23 Kelvin, far below the CMB temperature of 2.7 Kelvin. This means Phoenix A star is, right now, and for a very long time to come, gaining mass from the CMB rather than losing it. The universe will have to cool to temperatures below Phoenix A star's Hawking temperature before evaporation can even begin to dominate over accretion. As the universe expands and cools, the CMB temperature drops. This cooling takes an extremely long time. Only after the universe has expanded and cooled to the point where the CMB temperature falls below Phoenix A star's effective temperature, which requires expansion by an extraordinary factor, will the net energy balance tip from growth to shrinkage. In effect, Phoenix A star is one of the objects that the universe will build and then be unable to dismantle for timescales that make the current age of everything look instantaneous. It will sit there, long after the sun has exhausted its hydrogen fuel and swelled into a red giant engulfing Earth, long after the Milky Way and Andromeda have collided and merged, long after the last new stars in the universe have been born and lived and died, long after white dwarfs have cooled to black, long after neutron stars have emitted their last radio pulse into an empty, starless cosmos. Through all of that, across timescales that dwarf everything we know about cosmic history, Phoenix A star continues. And what does the universe look like when those timescales play out? Part 12. The Universe After Stars Die. We are currently living in what cosmologists call the stelliferous era. This is the age of stars, a phase of cosmic history that began with the formation of the first stars a few 100 million years after the Big Bang, and will end in the deep future when the last low-mass red dwarf stars finally exhaust their hydrogen fuel and fade to cold, dark remnants. The stelliferous era will last approximately 10 to the 14th years, roughly 100 trillion years. This is about 10,000 times longer than the current age of the universe, but it is a finite number, and when it ends, the universe will look radically different from anything we can observe today. Star formation requires clouds of cold molecular gas and dust. Over time, that raw material is consumed, converted into stars, stellar remnants, and the radiation those stars produce. The galactic gas supply gets depleted, star formation slows. The rate of new stellar births declines over billions of years, from a peak several billion years in the past to the present, already declining rate, to eventually near zero. The last stars to form will be the smallest and longest-lived red dwarfs with masses perhaps 10% of the Sun's mass, burning hydrogen so slowly that their lifetimes stretch to tens of trillions of years. But eventually, they too will exhaust their fuel. When that final red dwarf goes cold, the stelliferous era ends. And what remains? The universe at that point consists of the remnants of stellar evolution, white dwarfs, which are the electron-degenerate cores of stars like the Sun that have shed their outer layers, neutron stars, the hyper-compressed remnants of more massive stars that ended their lives in supernova explosions, and black holes, the remnants of the most massive stellar evolutionary pathways. Among all of these remnant types, black holes are unique in that they do not cool in the conventional sense. White dwarfs radiate their stored thermal energy and slowly dim over trillions of years, eventually becoming cold, dark objects called black dwarfs, though this process takes so long that the universe may not yet be old enough for any black dwarfs to exist. Neutron stars emit their rotational energy as radiation and gradually spin down. Black holes simply persist. This era, the cosmological future following the end of the stelliferous era, is sometimes called the degenerate era, while white dwarfs and neutron stars still exist in significant numbers, and the black hole era once those objects have been disrupted or decayed. During the black hole era, which begins on timescales somewhere around 10 to the 37th to 10 to the 40th years, the universe becomes dominated by the gravitational presence of black holes. Normal matter has largely dissolved, been disrupted, or been absorbed. The familiar structures of galaxies and clusters are long gone. The universe has expanded so much that regions that were once gravitationally bound have been torn apart by cosmic expansion, and the remaining black holes are gravitationally isolated, each one sitting in its own dark, vastly expanded corner of space-time, separated from others by distances that light could never meaningfully cross. In this era, Phoenix A star, or whatever the Phoenix cluster has become over those unimaginable timescales, is one of the dominant remaining structures in the universe. Not dominant by being active or luminous or visually spectacular, dominant simply by being there, holding mass, curving space-time around it, persisting in a universe that has otherwise largely dissolved its familiar contents. There is something profound and slightly disorienting about this picture. The universe we live in, filled with stars and galaxies, and the spectacular complexity of astrophysics that fills every telescope image ever taken, is, in the perspective of the universe's full temporal extent, an early and temporary phase, a brief initial moment of stellar ignition lasting 100 trillion years, surrounded on either side by enormously longer eras of darkness. Before the stars, the universe was dark and structureless. After the stars, the universe becomes dark again, inhabited only by remnants, and of all those remnants, black holes are the most durable, the longest lasting, the final objects. Phoenix A star, forming in that brief stellar era, will persist through every subsequent era of cosmic history and survive into the terminal epoch, the final, incomprehensibly long phase of black hole dominance, followed by the eventual slow evaporation even of the largest black holes, as the universe cools below their Hawking temperatures and the quantum thermal process finally tips from accretion to loss. The universe that Phoenix A star eventually evaporates into, if it ever does, on timescales of 10 to the 100th power years or more, will be a universe emptied of everything else, a space-time still geometrically curved by its presence, still measurably influencing the geometry of the universe in its vicinity, radiating photons at a temperature unmeasurably close to absolute zero, the last significant object in a cosmos that has otherwise dissolved to nothing recognizable. That is the long view, the view from the end. But if Phoenix A star represents this kind of cosmic permanence, if it is genuinely one of the last objects in the universe, then understanding what it actually is on the inside becomes one of the most interesting questions in all of physics. And on that question, the answer is, we do not fully know. Part 13. The strange question of the interior. Every introductory treatment of black holes eventually arrives at the singularity. It is the moment in every explainer, every textbook chapter, every documentary where the narrator lowers their voice slightly and says something like, "and at the center, physics breaks down." And that line is true. But it is also a little too clean, a little too comfortable, because it implies that physics breaks down in one specific place, at the center, and works fine everywhere else inside the horizon. The reality is considerably stranger than that, and for an object the size of Phoenix A star, the strangeness begins not at the center, but at the boundary, and it does not stop anywhere between the horizon and whatever is actually happening at the core. So let us walk through this carefully, because the interior of a black hole is one of the places in physics where the honest answer to almost every question is, we are not entirely sure, and understanding why we are not sure is more interesting than pretending. We are. The singularity, in the language of classical general relativity, is a point, or a surface, or a region, depending on the specific geometry of the black hole in question, where the mathematics of the theory produces quantities that go to infinity. Infinite density, infinite space-time curvature. The field equations of general relativity, which normally describe how mass and energy curve the fabric of space-time in a smooth, continuous, well-defined way, arrive at a location inside a black hole where the curvature becomes arbitrarily large and the mathematical description loses all predictive meaning. The equations, quite literally, stop working. They produce not just large numbers but infinite ones, which is the mathematical equivalent of a calculator displaying an error message. The theory is telling you that it has reached the boundary of its own applicability. This is not a hypothesis or a theoretical speculation about what might happen in extreme conditions. It is a proven mathematical result. Roger Penrose demonstrated in 1965 that under very general physical conditions, conditions that are almost certainly satisfied in any realistic black hole, the formation of a trapped region of space-time, which is what a black hole is, inevitably leads to geodesic incompleteness. Geodesics are the paths that particles and light rays follow through curved space-time. Geodesic incompleteness means that some of those paths simply end. They reach a finite point in finite time, and then there is nothing. No continuation. No further space-time to travel through. The geometry terminates. This is what a singularity is in the precise mathematical sense, and Penrose's proof that it must exist inside black holes earned him a share of the Nobel Prize in Physics in 2020, more than 50 years after the original paper. The mathematics was that solid. But, and this is a crucial but, the mathematics of classical general relativity does not incorporate quantum mechanics. General relativity is a classical field theory. It describes space-time as a smooth, continuous geometric object, and it describes gravity as the curvature of that object produced by the presence of mass and energy. It works extraordinarily well. It has been tested to extraordinary precision in a wide range of physical situations, from the precession of Mercury's orbit to the gravitational wave signals detected by LIGO. It is one of the two pillars of modern physics, alongside quantum mechanics. Quantum mechanics, the other pillar, operates on completely different principles. At small scales, energy is not continuous, but comes in discrete packets called quanta. The position and momentum of a particle cannot both be precisely defined simultaneously. This is Heisenberg's uncertainty principle, not a limitation of measurement instruments, but a fundamental feature of reality. Particles exist in superpositions of multiple states simultaneously, until a measurement forces them into a definite outcome. The evolution of quantum systems is governed by probability amplitudes, not deterministic trajectories. The mathematics is entirely different from general relativity, and the conceptual framework is essentially incompatible with it at a foundational level. Here is the problem. These two frameworks, each extraordinarily successful in its own domain, have never been successfully unified into a single, consistent theory. General relativity describes the large-scale structure of space-time. Quantum mechanics describes the small-scale behavior of matter and energy. In most physical situations, they operate in separate domains, and the lack of unification does not matter in practice. You do not need quantum mechanics to calculate the orbit of a satellite, and you do not need general relativity to describe the energy levels of a hydrogen atom. But inside a black hole, near the singularity, both frameworks become simultaneously relevant. The space-time curvature is extreme enough that general relativistic effects are critical. The density is high enough that quantum effects cannot be ignored. And when you try to apply both theories at once to the same physical situation, you get contradictions. The mathematics breaks down, not because one theory is wrong, but because two correct theories are mutually inconsistent when forced to operate in the same regime. A complete theory of quantum gravity, a single framework that seamlessly incorporates both general relativity and quantum mechanics, would resolve these contradictions and tell us what is actually happening inside a black hole near the singularity. That theory does not currently exist. String theory and loop quantum gravity are the two most developed candidates, and both have produced remarkable mathematical insights. But neither has been confirmed experimentally, and neither is complete enough to give us a definitive answer about the interior of black holes. The development of quantum gravity remains one of the central unsolved problems of theoretical physics, and it has been for roughly a century. What this means for Phoenix A star is not a minor gap in our knowledge. It means that for the most massive object ever catalogued in the observable universe, the extreme data point at the top of every ranking of gravitational structures, we genuinely do not know what is happening inside it. Not approximately. Not with some manageable uncertainty. We do not know, in the deepest physical sense, because the theory required to describe it has not been written yet. Let us sit with that for a moment. Phoenix A star has been sitting there for billions of years. It has been accumulating mass, consuming gas, merging with other black holes, growing to its current scale across a significant fraction of the universe's entire history. And the region inside its event horizon, a sphere with a radius of 2,000 astronomical units, a volume that would contain our entire solar system and significant portions of surrounding interstellar space, is, from the perspective of current physics, genuinely unknown territory, not unvisited, unknown. We do not have the theoretical tools to describe it completely. Then there is the information paradox, which adds a layer of conceptual strangeness on top of the incompleteness of quantum gravity, and which connects the interior of Phoenix A star to some of the deepest questions in theoretical physics about the nature of reality itself. Here is the setup. Hawking radiation, the faint thermal glow that black holes emit due to quantum effects near the event horizon, carries energy away from the black hole over astronomical timescales. As the black hole radiates, it very slowly loses mass. In principle, over an unimaginably long time, this process would cause the black hole to completely evaporate. Now, thermal radiation is by definition random and featureless. It carries information about the temperature of the emitting body, but not about the specific configuration of matter that went into creating it. A black hole formed from the collapse of a massive star and a black hole formed from the gravitational assembly of a cold hydrogen gas cloud would, according to the naive picture of Hawking radiation, produce identical radiation spectra once they reach the same mass and charge and spin. The specific details of what went into making them would be erased. But quantum mechanics says this cannot happen. The principle of unitarity, one of the foundational mathematical requirements of quantum mechanical evolution, states that information is conserved. The quantum state describing a physical system at one time contains, in principle, complete information about its past state and its future state. You can run the equations forward and backward. Information does not disappear. If black holes genuinely destroy information by converting the complex quantum states of infalling matter into featureless thermal radiation, then unitarity is violated, and one of the foundations of quantum mechanics is wrong. This is the black hole information paradox. Hawking raised it in the 1970s as a consequence of his calculation of black hole evaporation, and it has remained one of the central, unsolved problems in theoretical physics ever since. It is a genuine contradiction, not a merely philosophical puzzle, not a semantic dispute, but a mathematical inconsistency between two frameworks that we have strong independent reasons to believe are both correct. Something has to give. Either information is somehow preserved in Hawking radiation in a way that the naive calculation misses, or unitarity has to be modified, or the picture of complete black hole evaporation is wrong in some important way. Several frameworks have been proposed to resolve the paradox, and the most compelling ones are worth understanding because they change the picture of what Phoenix A star actually is, not just what is inside it, but what its boundary means. The ER equals EPR conjecture, proposed in 2013 by Juan Maldacena and Leonard Susskind, is one of the most startling ideas in recent theoretical physics. The name refers to two famous papers, both from 1935. The Einstein-Rosen paper introduced what we now call wormholes, solutions to the equations of general relativity, describing a kind of tunnel connecting two separate regions of spacetime. The Einstein-Podolsky-Rosen paper introduced quantum entanglement, the phenomenon whereby two particles can be correlated in ways that cannot be explained by any local hidden variable theory, so that a measurement on one particle instantaneously determines the state of the other, regardless of the distance between them. These two papers, published in the same year by some of the same authors, were describing phenomena that appeared completely unrelated. One was about the large-scale geometry of spacetime, the other about the small-scale correlations of quantum particles. The ER equals EPR conjecture says they are the same thing. That quantum entanglement between two particles is, at a deep geometric level, equivalent to a microscopic wormhole connecting them. That the quantum correlations and the space-time connections are not two different phenomena, but two descriptions of a single underlying reality. If this conjecture is correct, and it is currently supported by a significant body of theoretical evidence, though not yet proven rigorously, it has profound implications for black holes. It implies that the Hawking radiation emitted by a black hole is quantum entangled with the interior of the black hole through a network of Planck-scale wormhole connections threading the event horizon. Information is not destroyed. It is encoded in those quantum correlations, preserved in the entanglement structure connecting the exterior radiation to the interior state. Under this framework, Phoenix A star's event horizon is not a simple geometric boundary. It is a surface threaded by an incomprehensibly dense network of quantum geometric connections. Each Hawking photon that escapes carrying entanglement correlations with the interior through microscopic wormhole structures whose scale is the Planck length, approximately 10 to the negative 35 meters. The largest boundary in the known universe is, at the Planck scale, the most information-dense structure in the known universe. The holographic principle approaches the same problem from a different direction, and it produces an equally striking picture. The principle originated in theoretical work by Gerard Hooft and Leonard Susskind in the 1990s, drawing on earlier observations by Jacob Bekenstein about the entropy of black holes. Bekenstein noticed in the early 1970s that black hole entropy, a measure of the information content of the black hole, scales not with its volume, but with the area of its event horizon. This is strange. For ordinary physical systems, entropy scales with volume, double the volume, roughly double the entropy. For a black hole, doubling the radius quadruples the area and therefore quadruples the entropy, but it increases the volume by a factor of 8. The entropy is growing much more slowly than the volume. It is as if the information describing the interior is not distributed throughout the volume, but is somehow concentrated on the surface. The holographic principle generalizes this observation into a statement about the nature of spacetime itself. In any region of spacetime, the maximum information content of that region is proportional not to its volume, but to its surface area, measured in units of the Planck area. The interior of a region is not, in this framework, a physically independent entity from its boundary. The three-dimensional physics happening inside is, in a precise mathematical sense, equivalent to a two-dimensional theory living on the boundary surface. The interior is a kind of projection, a holographic image generated by the boundary physics, in analogy with the way a two-dimensional hologram can encode and project a three-dimensional image. This principle was given a precise mathematical realization in 1997 when Juan Maldacena discovered the AD-CFT correspondence, a duality between a theory of gravity in a certain type of curved spacetime and a quantum field theory without gravity living on the boundary of that spacetime. This correspondence has been one of the most productive theoretical tools in physics for the past 3 decades, generating insights in quantum gravity, condensed matter physics, and quantum information theory. Applied to Phoenix A star, the holographic principle says something specific and remarkable. The event horizon of Phoenix A star, that surfaced 2,000 astronomical units in radius, covering an area larger than the cross-section of our entire solar system, is not just a geometric boundary. It is a two-dimensional surface that encodes, in its quantum properties, all the information about everything that has ever fallen into Phoenix A star in its entire history. Every atom of gas from the cooling intracluster medium, every photon absorbed during billions of years of accretion, every smaller black hole that merged with it during the hierarchical assembly that built it to its current mass, every quantum state of every particle that has crossed the horizon, all of it is encoded, in principle, in the Hawking photons being emitted from that surface at a temperature of 10 to the negative 23 Kelvin. The rate at which that information leaks out is almost incomprehensibly slow. The total evaporation time for Phoenix A star is on the order of 10 to the 107th years. The information encoded in the Hawking radiation is not transmitted in a clean, readable form. It is scrambled across correlations between vast numbers of photons in a way that, in practice, could never be decoded by any realistic measuring apparatus. But in principle, according to the holographic framework, it is there. The information is preserved. The universe is not forgetting. What this suggests about the interior of Phoenix A star is deeply counterintuitive. The naive picture, a three-dimensional volume of space enclosed by the event horizon, containing a singularity at the center, with conventional spatial geometry throughout, may be fundamentally misleading. If the holographic principle is correct, the interior is not a separate physical entity from the boundary. It is a description generated by the boundary. The three-dimensional interior is emergent. It arises from the quantum information structure of the two-dimensional horizon, in the same way that three-dimensional images emerge from two-dimensional holograms. The interior geometry, including the singularity, may be a coarse-grained, approximate description that works well when the quantum gravitational effects are small and breaks down when they become large. If loop quantum gravity captures something physically real, the singularity itself may not be a true termination of spacetime, but a region of extremely high but finite curvature, where the discrete, quantized structure of spacetime at the Planck scale becomes relevant. In loop quantum gravity, spacetime is not a smooth continuum, but is fundamentally granular, made of discrete quantum units of volume and area at the Planck scale. At extremely high curvatures, this granularity prevents the infinite compression that classical general relativity predicts, and replaces the singularity with a region of maximum density, still extraordinary by any normal standard, but finite. The trajectory through the singularity, in some loop quantum gravity models, connects to an expanding region on the other side, a kind of bounce rather than a termination. String theory approaches the problem differently, embedding both general relativity and quantum mechanics within a higher dimensional framework where the fundamental objects are one-dimensional strings rather than point particles. In string theory, the singularity inside a black hole may be resolved by the extended nature of strings. They cannot be compressed to a true point in the way classical particles can, and the interior geometry may be replaced by a more complex topological structure involving higher dimensional objects called branes. Neither of these frameworks is confirmed. Neither produces a definitive, experimentally testable prediction about the interior of Phoenix A star that current technology could check. They are the best theoretical tools available, and they suggest that the classical picture of the interior, the smooth three-dimensional volume with a singularity at the center, is almost certainly an incomplete description. But what the correct description is, exactly, remains genuinely open. We have, sitting 5.7 billion light-years away in the constellation Phoenix, the most extreme gravitational laboratory in the observable universe, an object of 100 billion solar masses whose boundary surface encodes more quantum information than any other structure we know of, whose interior almost certainly involves physics that our best theories cannot yet fully describe, and whose very existence at the intersection of general relativity, quantum mechanics, and quantum information theory makes it simultaneously the most important known data point for the physics we have not yet written. Not slightly incomplete, not missing a few details at the edges, fundamentally, structurally incomplete in a way that a century of theoretical effort has not yet resolved. Phoenix A star is not just the largest object in the universe. It is the largest unsolved problem in the universe. And it has been sitting there, patient and permanent, and entirely indifferent to our frameworks for longer than the Earth has existed, waiting for us to develop the mathematics capable of asking it the right questions. We are not there yet, but we are closer than we have ever been. Part 14. The most important unknown, how it formed. We have established what Phoenix A star is, or at least what it appears to be from outside. We have walked through its scale, its extreme properties, its future, and the deep uncertainty about its interior. Now we arrive at what may be the most important unanswered question attached to this object, and it is not a question about the black hole itself. It is a question about history, about time, about whether the universe had enough of it. The problem is this: Phoenix A star has an estimated mass of 100 billion solar masses. The Phoenix cluster sits at a redshift of approximately 5.7, that is, the light we receive from it left when the universe was roughly 5 billion years old, meaning the cluster and its central black hole have been in place for at least that long. The black hole has been growing for some fraction of the universe's 13.8 billion year history, beginning from a seed of unknown mass at some unknown early epoch. Working backward from 100 billion solar masses using standard accretion models is deeply problematic. The Eddington limit sets the theoretical maximum rate at which a black hole can accrete mass while radiating at the efficiency required to support the energy balance. Accrete faster than the Eddington rate, and the radiation pressure from the infalling material overcomes gravity and drives the gas away, shutting down accretion. At the Eddington limited rate, a black hole can roughly double its mass every 40 to 50 million years, a process called the Salpeter timescale. Starting from a seed black hole of 1,000 solar masses, a generous initial mass for a population 3 stellar remnant, and accreting continuously at the Eddington limit for the entire age of the universe, gives a final mass of approximately 10 to the 22nd solar masses. This is absurdly higher than any observed black hole, which simply means that Eddington limited accretion is not a realistic picture of what actually happens. Real accretion is intermittent, inefficient in terms of available gas supply, and periodically shut down by AGN feedback. The reverse calculation, starting from 100 billion solar masses and asking what seed mass at what epoch is required, is what creates the problem. If Phoenix A star has been growing for the full 13.8 billion years of cosmic history at a realistic average efficiency well below the Eddington limit, then its seed mass at formation would need to have been extremely large, larger than population 3 stellar remnants, possibly larger than direct collapse black holes. Depending on the assumed average accretion rate and efficiency, the implied seed mass can become uncomfortable, pointing either to anomalously high accretion rates at early epochs or to seeds that were themselves already extremely massive. This is not a problem unique to Phoenix A star. The same calculation applied to the quasar-era supermassive black holes at high redshift. Objects with masses of several billion solar masses detected when the universe was less than 1 billion years old produces similar tensions with standard growth models. But Phoenix A star, at the highest end of the mass distribution, makes the tension most acute. The theoretical proposals for resolving this problem are several. Direct collapse black holes, as discussed in the JWST section, can provide seeds of 10,000 to 1 million solar masses without any preceding stellar phase, significantly relaxing the growth time budget. Super Eddington accretion, accretion proceeding above the nominal Eddington limit, can in principle occur if the radiation is trapped and advected inward along with the infalling gas rather than escaping outward. This process, called slim disk or thick disk accretion depending on the specific model, allows accretion rates several to perhaps hundreds of times the Eddington rate under the right conditions, dramatically accelerating the early growth phase. The most speculative, but perhaps most physically intriguing possibility is primordial black holes. If density fluctuations in the very early universe, during or just after inflation, before the epoch of nucleosynthesis, were large enough in amplitude to undergo gravitational collapse, black holes could have formed with masses entirely independent of stellar physics. These primordial black holes could in principle have masses ranging from tiny, already evaporated micro-black holes up to objects of enormous mass depending on the epoch of formation and the amplitude of the fluctuations. A primordial black hole of sufficient initial mass, accreting and merging through cosmic history, would face no formation timescale problem because its seed predates stars entirely. The concept of stupendously large black holes, sometimes abbreviated slabs in theoretical discussions, extends this idea to its logical limit, considering primordial black holes with masses potentially far above any current observational upper bound. Slabs would not necessarily be detectable through standard AGN observations. They might be quiescent, sitting in voids or in extremely rare environments, growing slowly over cosmic time. Their existence, if confirmed, would add another tier to the black hole mass hierarchy above Phoenix A star. For now, this remains firmly in the domain of theoretical speculation with limited observational support. What Phoenix A star tells us, as the current observational upper bound of the mass distribution, is that whatever growth process produces the largest black holes, it is capable of reaching 100 billion solar masses, and has done so at least once in the observable universe. Whether it has done so only once, or whether Phoenix A star is simply the most extreme example of a broader population of objects at this mass scale that are mostly invisible to current surveys, is a question that the next generation of observatories, the next generation of radio arrays, X-ray satellites, and gravitational wave detectors is positioned to begin answering. The formation history of Phoenix A star is, in some ways, the most fundamental question it poses. Not because the answer will change the object itself. Phoenix A star does not need our understanding to continue existing, but because the growth pathway to 100 billion solar masses is a test of the most fundamental processes in cosmology, how structure forms, how mass concentrates, how black holes and galaxies co-evolve. Phoenix A star is not just an extraordinary object, it is an extraordinary question. Part 15. Final collapse. What largest actually means. We have arrived at the end of the journey through Phoenix A star, and it seems appropriate to step back from the individual facts, the mass, the radius, the density, the evaporation timescale, and ask what the whole picture actually tells us. The question we started with was simple. How big is the largest black hole ever found? After everything we have covered, the honest answer is larger than any human intuition was built to handle, and uncertain enough at its edges that the word largest deserves some careful qualification. The mass estimate of 100 billion solar masses is model dependent. The event horizon of roughly 2,000 astronomical units is derived directly from that estimate and inherits its uncertainty. The claim of being the largest is contingent on the Brockamp et al. Analysis being correct, and it competes with other extreme objects, Holm 15 A star, Ton 6 18, others in the range of tens of billions of solar masses that may or may not rank below Phoenix A star, depending on which mass estimation method you trust most. And yet the qualification does not diminish the object. Even at the lower end of the plausible mass range, say 20 to 40 billion solar masses, Phoenix A star is one of the 2 or 3 most extreme gravitational structures ever identified. Its event horizon, at even half the Brockamp estimate, would still encompass the entire solar system and extend well into interstellar space. Its average density would still be below that of air. Its tidal forces at the horizon would still be undetectable. It would still outlive the stars by more orders of magnitude than the stars have outlived the Big Bang. What does largest mean for an object like this? We have seen that mass and size, while related in black hole physics through the Schwarzschild formula, do not correspond to size in the way we intuitively use the word. The event horizon is not a physical surface in the way a planet's surface is physical. It is a geometric boundary. 2,000 astronomical units is not the extent of a thing. It is the radius at which a specific relationship between space-time curvature and the speed of light is satisfied. The size of Phoenix A star is really the size of a mathematical condition satisfied by the space-time geometry surrounding a mass concentration. This distinction matters for the deepest interpretation of what the object is. We are not looking at a material object with a physical surface. We are looking at a region of space-time that has crossed a specific geometric threshold. The mass inside that region, whatever its internal structure, however it is distributed among the singularity or the whatever actually exists at the center, has curved the surrounding space-time steeply enough that the future light cones of every event within a certain radius are pointed only inward. That is the black hole. That is what Phoenix A star is. A region of curved space-time in which the future is structurally defined. The difficulty of understanding this has a direct bearing on the question of whether there is a largest black hole at all in any physically meaningful sense. The Schwarzschild radius formula does not contain a term that becomes undefined or infinite for very large masses. There is no obvious mathematical barrier in classical general relativity to black holes of arbitrarily large mass. The observational ceiling near 10 to the 11 solar masses is either a physical consequence of AGN feedback regulation or a detection limit. The theoretical framework of gravity itself does not prohibit larger objects. What may limit black hole growth in practice is the supply of mass available in the surrounding environment and the timescales over which accretion and mergers can proceed. The observable universe contains a finite amount of mass, approximately 10 to the 53 kilograms in ordinary matter, roughly equivalent to 10 to the 23 solar masses. A black hole accreting all of this mass, which is obviously not physically realizable, since most of that mass is distributed across billions of galaxies in no positional relationship to any single black hole, would have a mass of 10 to the 23 solar masses, with a Schwarzschild radius of approximately 1/500th of the current size of the observable universe. These are not physically plausible scenarios, but they illustrate that the mathematics of black holes does not care about the numbers we find large. The universe's upper limit for black holes is not written in the equations of general relativity. It is written in the equations of cosmology, the expansion rate, the matter distribution, the timescale of structure formation, the efficiency of accretion and mergers. Phoenix A star sits near the upper bound of what the cosmos has actually managed to produce within its current age, given its actual matter content and its actual history. Whether that is also the maximum of what the cosmos could in principle produce, given more time or different initial conditions, is a separate and still open question. And then there is the deepest inversion of all. We came to Phoenix A star with a question about size, about bigness, about the largest thing in the universe. And what the object has shown us, step by step, is that size for a black hole is not the same concept as size for a planet or a star or a galaxy. For those objects, size is a property. They have a measurable extent, a defined surface, a physically meaningful boundary. For Phoenix A star, size is a consequence. It is not a property the object possesses independently of the surrounding spacetime. It is the result of the geometric relationship between the mass and the threshold condition of general relativity. The size of Phoenix A star is the size of a physical law applied to an extreme mass. It is the embodiment of a mathematical condition in the structure of spacetime. This is the final reframing that Phoenix A star forces on every intuition we started with. We asked how big the largest black hole is, expecting an answer measured in kilometers or astronomical units or light years. And the answer is indeed measurable in those terms. 2000 AU, roughly 0.3 light years, roughly 65 parsecs for the diameter. But those numbers describe a geometric boundary, not an object's edge. They describe where space-time makes a certain kind of irreversible decision, not where matter stops. The universe's largest known object is not a thing with edges. It is a region where the future became constrained, a place where the geometry of space-time has settled into a configuration from which there is no escape, defined not by walls or surfaces, but by mathematics. And the question of its formation, its interior, its fate, all of those questions remain, in their various ways, open. Open in the sense that current observations do not fully constrain the answers. Open in the sense that current theory does not fully resolve them. Open in the sense that the frontier of what we know about the largest structure in the cosmos is also, not coincidentally, the frontier of what we know about gravity, about quantum mechanics, and about the long-term fate of space-time itself. Phoenix A star is not the biggest object in space in the way a mountain is the tallest object on Earth. It is the place where our map of the universe runs up against the edge of its own accuracy. It is the data point that sits at the boundary of what the current generation of theory and observation can reliably describe. And there is something appropriate about that. The universe's most extreme known object is also one of its most effectively hidden ones, defined by inference rather than image, by effects rather than observation, by what we cannot explain without it, rather than by what we can directly see. For an object that represents the limit of measurable space-time curvature, it is fitting that it also represents, in a certain sense, the limit of our current ability to measure. Something is sitting at the center of SPT CLJ 234-4-4243. Something is driving the cooling flow, inflating the radio bubbles, consuming the molecular filaments that ALMA revealed falling inward from the surrounding cluster. Something is registering as an energy imbalance in the X-ray data that has been accumulating for over a decade across multiple telescopes. That something is, by the best current accounting, the most massive single gravitational object in the observable universe. We have not imaged it. We have not measured it directly. We have not traced the orbits of stars around it. We know it in the way that a doctor knows a tumor from a scan before ever seeing it directly, through its effects on surrounding tissue, through the behavior it imposes on everything around it, through the unmistakable signature of something extreme working in the dark. One day, a telescope powerful enough to resolve its shadow will be built. One day, the mathematical framework of quantum gravity will be complete enough to say what is actually happening in the region of space-time it occupies. One day, the formation history that connects the early universe's anomalously large seeds to this endpoint will be observationally constrained by instruments we have not yet built. Until then, Phoenix A star sits there, 5.7 billion light-years away, hidden inside a cloud of X-ray emitting gas, patiently and utterly indifferently outlasting everything we have ever pointed a telescope at, waiting to be fully understood. It has been waiting for 5 billion years already. It will wait considerably longer than that. And the question it is waiting to answer, whether the universe has a physical upper limit to the scale of its most extreme structures, and what lies at the boundary of that limit, is not a question with an unimportant answer, because the answer, when it comes, will define something fundamental about the geometry of space-time itself, about what the universe is permitted to build, about whether the rules of physics contain, hidden inside their equations, a ceiling, or whether that ceiling is simply the edge of our current vision, and somewhere beyond the observable horizon, something is already sitting there at a scale that would make Phoenix A star look, in the mathematics of general relativity, like a rounding error in the opening terms of a calculation that the universe is still working through. We do not know which answer is true. That is, depending on your perspective, either the most unsettling fact in astrophysics or the most exciting one. I find it to be both.